Hey, hope you're all doing well. My name is Kogan Thangasudan, and before I start the masterclass, let's imagine that you spend millions of dollars and hours building, testing, and exploration rover to explore unknown environment and collect data. So after the rover is completed, its first mission is to explore and collect data from a distant planet, which could be millions of light years away. So let me show you an example. As you can see here, I have made an exploration rover simulation on Webbot. I use multi-layer persistent neural network to train the rover as a evolutionary robotic. So as you can see, during the training, the rover will learn the train safe path, which is indicated by the black outline, obstacles and extractors. And here is the run through after 2 generations. Like it did, is pretty good at following the line. It comes to a cylinder, it doesn't have just two sides, where it has multiple sides depending on how many, like what damage you did it at, as you can see here. So it does a massive oval rather than the small one, and follows the line here. But for a cube, it's perfect. It's only like two edges. But since the rover will be millions of light years away, you cannot 100% guarantee a stable connection to the rover. I don't get any cellular signal in my room, so I can't imagine having stable connectivity over millions of light years away. So imagine during the connection loss, the exploration rover is faced with uncertainty that will result in life or death. So as you can see here in the simulation, I will add an unknown obstacle like ray gun. So if the ray gun makes contact with the rover, it will disintegrate. So the aim of it is to avoid it. But as you can see on the simulation, it hasn't learned that thing or that object, so it doesn't know what to do. So it just ignores it. It thinks it's a unknown variant or a bug and just ignores that and just does what it's trained to do. So coming back to the slide, we need an autonomous system that will adaptively learn to reach its goal. In the case of the rover, it will be survival and how it will adaptively learn to survive when encountered with unknown environment. Therefore, I will be focusing my research in static adaptive learning, a game theoretical approach to navigating uncertainty. What do I mean by this? So in a sense, using game theory for adaptive learning when faced with uncertainty. To understand my concept of adaptive learning in terms of autonomous system, first I will cover information-based learning. Information-based learning is an idea of classifying a subject to its label, like object recognition classification, where the model matches certain objects' characteristic to output an object label. Here, as you can see, there is two approaches. First one is a machine learning approach, and the second one is the deep learning approach. So for a machine learning approach, it could be a thing as linear regression, where a feature or for a given object is extracted and put through a classifier, and if that set of features matches the current object, then it will output that specific option. Whereas in a deep learning model, which could be a neural network model, or in the example, it will be a convolutional neural network, a CNN, which will extract image, gets like a learned features from that set of objects, rather than manually giving the extraction. The neural network learns automatically to give the certain output. So in that case, it will be more efficient at recognizing a given object than a machine learning approach. Then moving on to relationship-based learning is the idea of forming relationship between the subject. Here is a research carried out by MIT. So as you can see, there is like a stacks of cubes. So as you can see on the first stacks of cube, you can see that the yellow cube is above the red cube, and that's true, and the green cube is above the blue cube. Using the first concept of information-based learning to identify the object, so it identifies the color of the object, and with that object it creates the relationship between them. So we know that we have a yellow cube as well as a red cube, and what's the relationship between it? The yellow cube is above it, so the relationship is above the red cube. Similarly, this could be applied to an NLP case. So here we have Paris Hilton bought 200 shares of Bank of America in 2006. So just in that sentence, we have the location company, or it could be a name, since Paris Hilton is a name, which makes more sense in the subject of the whole sentence. Then 200, a quantity. Bank of America is a company, but America is also a country, and 2006 is the time. So it's just a way of simplifying this and making the program understand or creating a relationship between this sentence. Or like as you can see from this sentence, it formed a relationship by allocating the specific category to it. So from these two, we could generalize adaptive learning. So the idea is to first use information-based learning to generate the object, or to recognize the object or any subjects that's been currently being presented. Then use relationship-based learning to link the given subjects together. So how does subject A relate to subject B? Like if it doesn't any have relationship, why is it here, there? Is it like, for example, wherever it's faced with the obstacle, you could say, was the obstacle is in front of the rover, so the relationship is in front. With the object being recognized and the relationship formed with the object recognized, we could perform adaptive learning on it. So my whole concept of adaptive learning will be split into three major sections. First one will be knowledge base, then game theory, then probabilistic verification. I will start by exploring knowledge graph. So traditional knowledge graph. Knowledge graph is a database that uses a knowledge structured format to store and interlinked information, allowing for complex relationship and context to be represented and easily understood. So here is an example. In traditional knowledge graph, we have nodes, links, and edges. So here we can see that dog is an animal, cow is an animal as well, and animal is a living thing. Same as herb is a plant and plant is a living thing. But also cow eats herb. So here, as you can see, the arrow shows the relationship, and the nodes contain the subjects. In my case, I'm trying to make a dynamically adapting structure. Why? Because imagine case of the rover, it will continue to move to explore and move within the terrain. As it moves, new subjects or new objects will be introduced into the knowledge graph. So the idea is to create relationship that makes sense between the nodes. So like all knowledge graph, my data structure will also identify all the nodes, initialize the relationship between the nodes. But the key difference will be finding any hidden nodes. So for example, given node A, B exists, C should exist, because it's the idea of common sense and logic. Since new nodes being introduced, we should re-evaluate the relationship, and as the existing relationship also changes. The main concern to keep in mind is that since more node is constantly being introduced, how would I handle any inconsistent data or any ineligible data as well? So here is an example of my dynamically adaptive knowledge graph. This model could be applied to the case of NLP as well. So given the sentence, Dan likes his wife and George does too, we can say that since I liked then Dan and wife of Dan. So from that sentence we could say since Dan likes his wife, then we can derive the second half, which says that George, which says that George likes wife of Dan, or George likes his own wife, right? Because from that sentence you could derive these two things, because both of them make sense. So it's the idea of having common sense and a logic. But the problem is with the current NLP segmentation solution, it doesn't derive this, because when we put it into like our case of knowledge base, right? Let me just use another page. So let me just have the sentence here so you can see. Right. So with this, we have what's it? A set of subjects, right? First will be Dan, then the second one will be George, since these two names are mentioned, and third one that's obvious is Dan's wife, right? Dan's wife. So these are nodes. If you put it in a knowledge base, if you think about it. So we know that the relationship between Dan and Dan's wife is likes, same with George, right? Likes. We don't know the relationship between George and Dan. We don't know that. It hasn't given it on the sentence. But the problem is there's another subject that as a human makes sense. But how can a computer or an AI derive this? Like, this is the hidden node that I was talking about. So this is the question. Oh, you can't see. So this is the question that we need to answer. So how do we get this hidden node? And so with my proposal, it tackles this as well. So in the end, whenever with the perfect solution, we will get this as well. We'll have this link. But currently, this doesn't exist. And that's what I'm trying to solve. So yeah, hope that makes sense. This is just an NLP application, and it's easier to understand just with this sentence rather than just with that sentence, rather than just explaining it with like a rover and just creating a hypothetical environment verbally. Moving on, since we have a core structure, a data structure of a knowledge based graph with the relationship and all the nodes, subject or player, whatever we call it. With that information, we could apply it to game theory. So let me just start by introducing what is game theory in a traditional sense. So game theory is a field of mathematics that studies strategy interactions between decision makers, analyzing how they make choices in situation where their outcome depends on their actions for others. And here is a popular scenario. It's called the prisoner's dilemma. So imagine there's two prisoners, A, B. The idea is that when two of them confess their crime, they get 5 years each in jail. If prisoner A confesses and prisoner B doesn't, stays silent, prisoner B gets 20 years, so he's like backfires by remaining silent because he wasn't being truthful. Whereas the opposite happen if prisoner A stays silent and prisoner B confess, then A stays in jail for 20 years. Whereas if both of the prisoners remain silent, it's only 1 year. So in the ideal situation, they both should stay silent, so they get the least amount and a fair deal. But the problem is, how could you control in a real life situation? How could you control what the human is thinking? Because now this will introduce like a cat in the box concept, or like the paradox. So like the question I will ask you guys as the audience, or the thing to consider is, what is the best possible outcome, and how could you decide, or which prisoner benefits the most depending on the outcome you chose? Well, what constraint could you apply to make the outcome possible? So just have a think about that. So going back and just talking about how does game theory interacts with AI, like the autonomous system. So game theory with AI and multi-agent system is a study of strategic decision making in environments where multiple artificial intelligent agents interact, focusing on how these agents can optimize their decision while considering the action and interaction of others. In my model, the game theory will identify all the agents, which will be the nodes. Also, also have the agent's aim. What does the agent want to achieve? what is goal. So in terms of the rover, it's for survival and simulate all the different possible scenarios or gameplays. If you put it in that sense, it's like just generate, because since the situation is unknown, it doesn't know, it doesn't have a hardcore solution. So it has to generate or simulate different possible outcome using some sort of reinforcement learning with multi-agent interaction, and just simulate different possible scenarios that could occur. With those set of simulation, we need to narrow it down to the best one. So this will introduce so we need to introduce some sort of verification. I like to incorporate probabilistic verification. So initially, a model verification is the process of ensuring that a computational model accurately represents the intended design and logic, and that it correctly implements the specified algorithm and functionality. So given the system will have a finite state model. Similarly, the system requirements will put into a temporal and logic specification, which both will be run through a model checker, such as spin or SMV. A model checker spin could also be implemented on Promula if anyone has used it, and this will result in the results of pass or fail, or if it is right or wrong. And if not, you could do counterexample and error trace. A breakthrough on verification is the idea of rational verification. It's the process of analyzing and verifying the behavior of agent in the system to ensure that ensure they act logically and optimally based on their knowledge, preference, and the strategies of the other agents in the environment. So the most popular model checker, or the world widely used, is Prism, and when in terms of rational verification, it's Prism 4, which uses LTL inputs, I believe. So here is an existing probabilistic model checker with Prism Games that just been recently that's recently been out. So with that, the thing is, you have the set of system. With the system, they have the probabilistic model. So imagine that's like knowledge base, but everything is in a probabilistic term rather than a relationship. So the relationship will probability value. Similarly, we have the system requirements and the probabilistic temporal logic specification to verify if the current system matches the specification in terms of the temporal logic. So with those, you could you put that through the probabilistic model checker, and it will either gives a right or wrong, or a quantitative result where it gives you a range of it could happen. Then a counterexample. Where in my case, we can't, my initial probabilistic model won't have any probability, so I can't use a probabilistic model and just create the probabilistic temporal logic specification based on the requirement and just apply that for in a Prism game or something, right? In this project, we have the simulated possibilities. With that, all the possibilities, check if the aim is achieved. Okay, if the aim isn't achieved, there isn't any point in even considering that approach. Then if it has achieved, then we could check the robustness, check the accuracy, and the probability of success, since the highest probability will be considered out of the list of different simulation and will be applied to the current model. The idea is to use rational verification as the backbone of probabilistic verification to consider the agent's preference and the impact it has from different experience. So why do this? The idea is to help any autonomous system deal with scenarios or situation it has no prior knowledge of, or to survive and not let people's hard work just disappear. For example, like in terms of the rover, like the researchers would spend millions of dollars and time, like even building one rover takes minimum like 5 years. So that time, and you cannot buy time, and with a minor error the whole thing could fail. So with adaptive learning, you're sharing the responsibility for that. It's just like a counter measure before just letting go. Say if the signal fails, you don't just let the rover just die if it's faced with like a life or death situation. It's like a last measure before it fails, because the worst case is that it just dies or it disintegrates and you can't do anything about it. But just before that, the idea is for the rover to have a chance of analyzing the situation and coming up with a solution to achieve its aim of survival. So from this whole presentation of the masterclass, what to take? So the thing to take is the whole concept of adaptive learning that I have derived from information-based learning and relationship-based learning. So it's the combination of those two learning we could use adaptive learning. So with the adaptive learning, that will use the data structure of knowledge graph to contain all the information of this environment, the agent, and anything that currently impacts its current situation. Then using that generated knowledge graph into a game theory approach to generate different simulation of possible ways to achieve its aim. All those possible simulation, we will apply probabilistic verification to get the best one for the current optimus system to perform when faced with uncertainty, to optimize its chance of achieving its goal. That's it. Thank you. Hope you enjoyed. And here are some papers that I would recommend if you're interested in this topic.